Alright, welcome everybody. So today I'm going to talk to you about electronegativity, some properties of the elements, and then some of the reactions. So electronegativity, it's going to have the same trend that you're going to find when you actually do ionization energy. So when you go down a group, the electronegativity is going to decrease. When you go across a period, the electronegativity is going to increase. Remember, electronegativity is the attraction an atom has for electrons in a bond. So if we put the Y into that context, remember as you go down a group that the atoms are getting larger. This means that electrons from other atoms in a chemical bond will be less attracted to the atom's nucleus. So this is, kind of like the shielding effect. There's these shielding electrons. They're shielding not only the atom's own electrons, but also electrons from another atom. When we go across, we have the opposite effect. We have atoms that are smaller. Because of this, electrons from other atoms in a chemical bond will be more attracted to the atom's nucleus. Now the other thing is this. Remember, electronegativity, it's a scale that's made up. It doesn't have those same, ionization energy trend exceptions. And because of that, we see a very smooth trend when we go down a group and when we go across a period. Now, something that sounds like electronegativity is electron affinity. And electron affinity is something that's actually measurable. It's measured in kilojoules per mole. And this is the energy change when an atom gains an electron. And so it could either be positive or it could be negative. And when you're negative, it means that you are becoming more stable. That means that you are releasing energy. So when an atom gains an electron, if it releases energy, its stability would increase. What we see is that when you go left to right, that the electron affinity generally becomes more negative. Now there are some blips along the way though, some exceptions like we see with ionization energy, and one of them, for example, is in group 2. Another one is in group 15, and another one is in group 18. In group 2, these all have NS2 as their valence shell. And so if we were to add an electron, it would have to go to the next sublevel, NP1. That requires energy to put an electron in a higher energy or sublevel. And so that would then lead to a positive electron affinity. We see the same thing with group 15. Group 15 is NP3. Well, if we add an extra electron, we become NP4. Now we're forcing this repulsion. And when we do that, that would increase the repulsion and we'd get a positive electron affinity. It would become less stable. And the same thing with group 18, that's NP6. Now, when we put the electron into the next energy level, it would go into N+1, really, because it's a next energy level up, and then S1. And so now we're putting it into a higher energy level. This is one of the main reasons why the group 18 elements don't gain electrons. Remember we talked about with ionization energy why they don't lose electrons. It's because they have such a high effective nuclear charge. Well, why don't they gain electrons? Well, that has to do with the idea that it takes energy to put them into the next higher energy level. Okay, so properties of different elements. When we look at the properties of the elements, I'll just list them here. We have metals. They are ductile. Let's move this down. Ductile, malleable, They conduct electricity. They have low ionization energies, low electronegativities. They have large radii. And so these metallic properties, these metallic characteristics, they tend to cause metals to lose electrons easily and form positive ions. And when I look at a nonmetal, they have a lot of the opposite properties. They tend to be brittle. They tend to be non-conductors, though there's some exceptions to that, like graphite. They tend to have high ionization energy, electronegativity, and a small radii. And they tend to gain electrons and form negative ions. And these are going hand in hand with each other. You know, the metals, they are losing electrons. Well, who are they losing them to? They're losing them to a nonmetal. A nonmetal gaining those electrons and then becoming a negative ion. Took those electrons from a metal who lost its electrons and became a positive ion. The metalloids are somewhere in between. So transition metals or transition elements, these are elements that have 3 through 11 on the periodic table in those groups. One interesting fact about them is that they form colored ions in solution. The most famous of them are copper +2, having this beautiful blue color, manganese +7, this deep purple color, cobalt, I think it's +2 as well, or +3. This has this beautiful blue color. In fact, this paint here from Starry Night is using cobalt blue. If you go to the art store and you pick up some cobalt blue, you'll see it's really kind of expensive. It's about $30 for a small tube of it. Alright, specific details about some elements. So cesium, francium, these are the most reactive metallic elements. On the other side, in the upper right, we have fluorine, oxygen. These are the most reactive non-metallic elements. Something like copper, gold, silver. That was actually silver, gold. These are sometimes called the noble metals. They rarely react with any other elements. They are, especially useful in something like jewelry. Copper is the most conductive element out there, and it is used in electrical wiring. But as they are being used more and more by humans, their rarity increases. Their price goes up. The ability to find them goes down. Another interesting element, carbon. Carbon actually has 2 allotropes, graphite and diamond. And what's so striking about these is that graphite tends to be a soft compound that's black, and it also has good conductivity, rare for a nonmetal. Whereas diamond is the hardest substance that's known. So here's the same element, but its structure makes them very, very different, have different properties. Okay, this is just for you to look through some common Latin names versus the common name. Some interesting ones like argentum. If you know the name Argentina, the country Argentina, that means the land of silver. Gold with its aurum Latin root, meaning to glow, and if you look at gold, it has this glow to it. When we talk about ion-electron configurations, there's ones that I want to focus on in the transition metals. For example, if we look at iron iron, if we look at it, it has argon and then 4s2 3d6. But when it becomes Fe plus 2, it won't lose from 3d, it loses from 4s, and that's for all the transition elements. So this will become argon 3d6. It loses the 4s first. And when it becomes Fe plus 3, it now will then start to lose from the 3d. This is why these transition elements can have multiple positive oxidation states. It's because they can lose from both their 4s and their 3d, or their 5s and their 4d. From both their s and d orbitals, they can lose electrons. If you want, you can try one for this, like we could do, you could do something like manganese, and you could do manganese plus 2, manganese plus 3, and manganese plus 7, and you could try those out and see how that goes. Okay, the reactions is what I want to finish with quickly here. So the alkali metals in water, any alkali metal in water, I'll use lithium for example, when you add it to water, it will undergo the same reaction, which is to form a hydroxide and to form hydrogen gas. This hydrogen gas is what catches on fire and gives you that real explosion when you put an alkali metal in water. You can go ahead and balance it and maybe write the net ionic formula. We'll discuss it in class. Halogen and metal. So halogen, you could do any halogen like fluorine, and we could do any metal like sodium, and what we'll see is that this will form a compound NaF. Again, you could balance that for me. Anionic single replacement of halogens. So the halogens, we have F2, we have Cl2, we have Br2, and we have I2. And so what happens is the F is the most reactive out of all of them. So if I put F2 with any of these, if I put F2 with something like NaCl, well, the F2 is reactive enough to replace the Cl, and we'll get NaF plus Cl2. If I have something like bromine, bromine is not as reactive, so bromine can only replace something like iodine. So bromine, we can have that replace NaI, and then we would have NaBr and I2. Now if I put iodine with any of the other elements, iodine with chlorine for example, just make this iodine with chlorine for example, in the chloride, there will be no reaction. So it's important to know that when we look at the halogens, the most active of them is fluorine. It can replace any other halogen in a compound. Chlorine can only replace bromine or iodine. Bromine can only replace iodine. Iodine can't replace any of them. Metal oxides in water look a lot like alkali metals in water. If I put Li2O in water, it will form a hydroxide. The difference is there's no hydrogen. And again, you can balance this. Non-metal oxides in water form acidic solutions. So something like SO2, commonly given off by coal-fired power plants. This is the sulfur dioxide. It combines with the moisture in the air and it produces that nasty acid rain, sulfurous acid. We could have something like CO2. People are talking about acidification of the oceans with the increased CO2 in the atmosphere. Well, this CO2, it combines with the ocean water, it forms H2CO3. This acidification of the water in the seawater causes things like dissolving of crustacean shells, which are mostly carbonate compounds. So this is some scary stuff going on here. This is environmentally impactful for you to think about. Alright, that's periodic table. Hope you like this video, and have a great day.